Okay, last time we talked about double Fourier cells and certain parameterizations of double Fourier cells through some factorization schemes. I want to recall something about from the last time, and so here is a file for lecture 5, but I want to start from the lecture 4 and state some and recall what we talked about, starting from factorization schemes. Double Fourier cell is parameterized by the two elements of the Weil group, which is in our case it's just a permutation group. You denote so these elements are usually denoted by U and V. So first Weil group is a permutation group, and I denote its generators with bar. Second Weil group is just permutation group. And corresponding Fourier cells, first one is correspond to barrel subgroup B. It will be usually group of upper triangular matrices. And second subgroup is B minus. It will be usually a group of low triangular matrices. Now for each, if we fix U and V and fix reduced word which correspond to U and V. So fix reduced decomposition of the corresponding element UV in the product of simple reflection in this double Weil group. So to such a reduced word, we assign a product. The product goes like this. So first we take product of all Cartan generators, and then if we have element like S, we write E, generator E, which is just upper triangular matrix with it has ones on the diagonal and one upper diagonal. And if the corresponding selection is S bar, then we write E bar, or it is the same F, same as F. So this will be low diagonal matrix, with one unity below diagonal. And in this way, we can construct the product of H's and E's. This is some sort of, and as I stated last time and repeat today, and this will be a certain parameterization of the Fourier cell. Word parameterization is a bit vague, maybe, so I'm not claiming this is so this will be coordinates, but I'm not claiming this will be global coordinates, that any element of the double Fourier cell have such factorization. But an open subset, yes, generic element have such factorization. Okay, so some examples of the theorems is such. So if we start for given U and V, we obtain the element from the double Fourier cell. Okay, this is a theorem. We have a map from the C star to the double Fourier cell, and this is rational isomorphism. I didn't prove it at all last time. I put some hints about proof in the notes and some problems, and we will. I hope you will enjoy it. Look into the problems. But the most maybe important part of this cluster theory business is not just some coordinate set, but transformation of the coordinates, which are mutations. In terms of our parameterization, these mutations lead to some relation between generators which we use in our parameterization. These generators are H's, E's, and F's, and here is a list which now takes a whole slide. And I stated these relations are equivalent to mutations, but now mutations not in terms of A coordinates, which we had in the first lectures, but in terms of, it is another type of mutation in terms of X coordinates. I'm quickly recording what was the last time, but with the hope that I'm improving something, which is of course not for sure. But is there any questions? Please feel free to ask. Now, in order to have some cluster story, I need to have some combinatorial data like quiver and algebraic data. So algebraic data will be this axis, which appear on this factorization, and combinatorial data will be the quiver constructed as before. So vertices of the quivers will correspond to the faces in this diagram. And the rule is as follows. So for each hi will correspond to the face which lies between the i's and i+1's horizontal lines. And we label them from the left to the right. So maybe it's better to explain on the example. So here is some, not easy, of course, word in double L group. So first we have product of S bars, S2, S3, S1, S2, S1. Then we have product of S's, S1, S3, S2, S1. Here is the corresponding factorization scheme. So first we take all H's, then here we have S2 bars, so we take F2 and H2 of some additional variable, then F3, H with some additional variable, and so on. Now, how I assign this axis to faces? So first we have X1. This H1 of X1, so it should be between first and second lines. So the lines are labeled from the bottom to the top. So here is X1. Then H2 of X2. Here is X2. Here is X3. Here is X4. Then we have X5, H2 of X5. So because it is H2, this X5 should be assigned to the face which is on the between second and third lines. And because this is the second H2 which we have in our word, this face should be second here. So here it is X5. Then we have X6, it should be here, X7 here. So this is the rule. It is easy to see that everything agrees. So if so, the number of axes, the number of axes is just equal to the number of faces, and moreover, the number of axes with the index say I is equal to number of faces between I and I+1. Indeed, if we have somewhere H2 of X, then we should have F2 or E2. So before we should have such slanted H or such slanted H. So we have one more face. So we have F2, which somehow close on face which we have before and opens new face. And this X goes to new open face. Okay, this is a rule. And how we assign axes to faces, and then we can construct quiver, and the rule for the quiver is as was on the before. Recall that our network is bicolored, so it has the vertices of black and white color, and we write arrows. Two faces are connected by arrows if they're incident, and the direction of the arrows goes clockwise around black vertices, and counterclockwise around white vertices. As before, faces which are not bounded, in some sense, should be viewed as frozen. So, in principle, one can write some edges here, but these edges probably have no clear meaning, and they do not appear in mutations, which we will consider. If time permits, today I will talk that somehow the edges should be viewed as half edges. Okay, and if we now, so for such picture, we have quiver. I don't know, maybe it will be useful if I draw some edges, but so this. You see here, these two edges actually cancels each other. It can happen. It's also easy to see that for each phase, ingoing and ongoing edges goes one by another. So here's outgoings, here's ingoing, outgoing, ingoing, and so on. This, of course, follows from these rules. So taking summing all together, so we see that from this from the vertex which correspond to the variable x8, we have 3 outgoing edges and 3 ingoing edges, and these 2 can be just cancelled. Okay, this is just part of the, because it's hard to stop. Here's this. No, the last one was incorrect. Okay, maybe there are many. And okay, and if we know this quiver and x variables, we can define mutation. And formal definition, which appears somehow without motivation, I should confess, but there is motivation, that it goes like this. So for pair Q and set of variables x1, xn, mutation for quiver goes as before, and for this x variables goes like this. So variable number k just inverses, and other variables are just multiplied by something some binomial which depend only on k. So 1 plus xk some sign, so either xk or xk inverse, in some power which is a number of errors from j to k. So this is no longer Laurent polynomial. It can have denominators like 1 plus x, but it is still positive. We don't have minuses in this expression. Okay. Any questions so far? Okay, so these mutations satisfy properties as before, and the theorem, which we left as a problem, is to show that any braid move, which correspond to braid relations as a double wire group, is correspond to mutation of these x variables. Here's an example of SL2, which we computed, but maybe it can be seen without manipulation. Okay, this is all what I want to recall from the last time. And now I want to say something which is even wasn't hinted last time. So this will be the part of the now lecture 5. I have a couple of prepared slides, and then I will start writing. So first of all, I want to talk about again about positivity. We have a notion of the totally positive matrix. This is a matrix such that all its minors are positive. It's very similar notion. There is a very similar notion, obvious generalization, totally non-negative matrix. Matrix totally non-negative if all its minors is non-negative. Note that here I assume that matrix belongs to GLM. So, for example, its determinant should be positive, non-zero. from the first glance, should be, one can think that there's no big difference between non-negative and positive, but actually there is a difference, because when you, for example, study some criteria of the positivity, you express some minors through other minors, but sometimes such expression require to divide on some minor. If the minor is 0, then there is no formula. So actually, story about a totally non-negative matrix is significantly more interesting than story of the positive matrix. For example, this double Brias cells appears in the story very naturally. So I denote by G greater than or equal. Maybe I should write 0 here. Sorry. The set of all totally non-negative matrices. And I denote that CUW greater than or equal to 0 intersection of the double Brias cell with a set of totally non-negative matrices. Since the whole group is a union, disjoint union of double Brias cells, then the subset of totally non-negative matrices is the joint union of the positive or totally non-negative double Brias cells. Theorem says the following, that if we take some reduced decomposition of UV and take the corresponding factorization formula, then this factorization formula defines a bijection between set of between tuples of k plus n positive real numbers and points in totally non-negative double Brias cell. So, let me now point some difference between complex case and this positive real case. In complex case, it was a birational map. This was not true that it was not true that any element of the double Brias cell have such decomposition. It was true in open subset, and if you consider all decomposition, it was true up to dimension 2, so it is very good, but I'm not claiming that all. But here, just you can take any decomposition, and this is a bijection. Part of the explanation is follows, that before you can take one decomposition, can take another decomposition, and they're related by mutations. They're related by braid moves, but in terms of cluster, they are mutations. And if you do mutations in this cluster variables, you quite often have factors like 1 plus x, factors like 1 plus x. Just in the definition, maybe in this formula, you see it's 1 plus xk, or 1 plus xk inverse. And if xk is equal to -1, then this is not either you get 0 denominator or in numerator, so the map is not invertible. You have problem. But since here we have everything is positive, you don't have any. Your variables are not equal to -1, so everything is okay. There is no at least problem which we had before. Okay, and one more remark is the following. So there is a open double Brias cell which correspond to the longest elements of the longest elements in the double viral group. This is W0, W0, full permutation. And so this in this case, this subset, we have no vanishing minors. So in this case, actually, totally such matrices, how to say, maybe I put it as a problem, maybe it's not completely obvious, but one can show that on this set, all minors are actually positive. So the totally non-negative matrices which belong to this largest cell are just positive matrices, this open subset. And hence, x coordinates, the coordinates which we use in our factorization scheme, provide another positivity test. So in order to check whether the matrix is totally positive, one can take its factorization, look to the corresponding coordinates, and just check that they are all positive. As I said in the end of the previous lecture, there's actually a relation between this x coordinate and minors. So in some sense, it's closely related test of positivity, but at least it's stated with a difference. Okay, maybe example. Let us consider the simplest case of GL2. We have our while group in this case is S2 times S2. It has 4 elements. Identity, identity, S bar identity, identity S, and S bar S. I don't know, I can write S1 here if it is, because it's a bit more correct, but we have only one reflection, so it's fine. Here are the corresponding words. So if identity, identity, then we have no E's, no F's, just product of the Cartan elements. If we have as a bar, then we will have one F. If we have just S, one E, and here I choose the reduced decomposition, suggest first we have S1 and then S. So this is a corresponding decomposition. And one can multiply matrices, and this is a result. What can I also comment formulas here? So, for example, look at this matrix. I claim that this matrix is totally positive. So you see, it's clearly all its minors are positive, but also if you compute its determinant, then it will be x2 times this x1, x2, x3, x4. So it will also be positive. And vice versa. If you take any totally positive matrix, you can find this axis if you know this, this, and this, and determinant. Product of this and this. Then from this data, you can recover all this axis. So in this sense, we have a bijection between R plus in power 4 and totally positive matrices 2 by 2, and this bijection is given by this form. What else? If you have a totally positive, so if you have totally non-negative matrix, so if it's totally positive, it belongs here. Here we have cases where this or this minor is equal to 0. It is impossible for totally positive matrices. It is impossible to have, for example, this minor equal to 0, totally non-negative matrix, because in this case, because these two numbers are positive, determinant will be negative, which contradict to the conditions the matrix is totally positive. So these two minors are non-zero, and either this is 0. So we have exactly 4 cases, 4 cells, and here are the parameterization. Okay.
Is it true in general that all cells which are not do not correspond to the longest element have like 0 minors?
We had a theorem last time. I don't know, maybe is it answers whether it's answer a question, maybe not, but which says the double Bria cell is determined by the condition that some minors are equal to 0 and some are not. So if you take not largest double brass cell, then some minus should equal to 0.
Okay. Yes, it answers.
More questions? Okay. I'm not going to prove this theorem in full generality, but I'm going to explain why this map is well defined. So why the matrix which obtains through factorization is totally non-negative. I mean, because this explanation has some idea. And, in order to do this, I have to impose some orientation on my network. Orientation will be defined, will go like this. So for horizontal edges, horizontal edges, okay, all edges will go from left to the right. So for horizontal like this, for slanted like this and this. Maybe for completeness, I can put orientation on the horizontal edges here. You can note the following property of this orientation, that on black vertices we have one outgoing edge, and for white vertices we have one ingoing. So some black vertex like this. In our case, I simplified everything, so actually all my edges have valency 2 or 3, so this condition is not extremely, it does look extremely deep, but actually this is a condition which appears quite often in such stories, so I prefer to spell it. This is what happens. Sometimes this is called Postnikov orientation. Maybe I should put his name here. Okay, here is an example, which I mean, I draw once and then repeat every time, where I need something like this, some example. As before, you have 5 S bars, 4 S's, and here is the orientation. I should confess that probably I didn't draw all orientations on all edges, but I hope the story is clear. And now I assign also weights. I assign also weights to these edges, such that the factorization matrix which we have here, each matrix elements are just the weights for the number of paths which goes from I to j. The weights are assigned as follows. So for each slanted edge, the weight is 1. And if the weight is 1, I just don't draw it. And then if we have some diagonal matrix, say x1, then for diagonal matrix, diagonal shift edges for the horizontal lines. How to say it? also this should be x4, but maybe this is not explanation. Let me recall you that H1 is a matrix, H1 of X is a matrix of X 1 1 1. Therefore, I wrote that weight of this H is X1 here, and here I put ones and just don't draw. Then I have H2 of X2, draw X2 and X2 here, and so on. So this theorem should be obvious after some point of considering it. So if you take this matrix element, so you want to come from some 2 to some other number, say 3 here. Then you go, if you take H, then H is diagonal, and if you have F, then you increase your index here and here. If you have E, you decrease your index. And you start from 2 and end on 3. So this is exactly matrix element which you want to consider. Okay, maybe I should write a bit more. So for matrix Hi of X, I assign the following picture. So here are some i's, and here weights are X, 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 here 1, 1. And matrix Hi of X is equal to, let me recall, it equal to X, X, and then 1. So I assign weights to edges. Weight of the path is a product of the weights of the corresponding edges. And that's it. So this statement is, how to say, is a lemma, or better observation. And the next statement will be theorem due to okay, I wrote Lindström, Kessel, and Vienno. I will write full names, which says that so if E is a matrix of paths, then its minors are also count the passes, but now you should consider sequences of non-intersecting passes from I to J. Maybe I should change here order. Maybe nobody care, but now I believe I should change. Okay, let me put the theorem on the next page in order to have some space. And corollary means that this matrix, path matrix E, is totally non-negative. Because if for each path, its weight, it's some monomial. If you have a set of passes, then its weight, it's a product of weights, so it's also some monomial. Therefore, this sum is a sum of monomials. It either positive or maybe 0 if there is no monomial, there is no passes which goes like you want. But anyways, this is a totally negative matrix. And this follows from the path interpretation of the product of the matrices. It's funny, but I again think I should change ing. Okay, I will double check. I am absolutely sure about this idea, but do not confuse matrix and transpose matrices. Sometimes difficult. Okay. Isaac, any questions?
Where we had definition of this EIJ, I missed this moment.
E is a matrix, is this matrix, and EIJ it's matrix element. And here is the index. I mean, which okay, let me delete this index.
So we correspond matrix to hold this picture, which is example.
Yes.
And then we okay, I understand.
Other questions? So what I'm claiming is that that if you choosing the path in this network is the same as multiplying of the matrix, multiplication of the matrix. Because our matrices are so simple. So if you have some e's, and you just look at this block, which just goes either horizontally, so the identity matrix, or just one on this picture below diagonal, and so on. Okay, up to the possible problems with transposition, I hope everything is okay. And now I want to switch on a light in my room and I'll continue. Okay. Now I start somehow a new topic, and I want to talk again about this x coordinates. Now recall that we can I don't know what to recall. Okay, let's. So when we talk about cluster algebras or cluster varieties, we have two types of data: combinatorial data and algebraic data. So combinatorial data is given in matrix Bij, which I assume to be antisymmetric. Quite often, it is more convenient to write down the equivalence set of this. Sometimes we have frozen variables. These are variables in which we do not perform mutations. So we have some set of variables 1 to n which are unfrozen, and then n plus 1 m which are frozen. If we mutate in frozen variables, in unfrozen variable, then the formula is like this. So xj, I will talk now for x mutation, xk is the power some sign, and here some bgk. So in order to be this algebraic function, we need this b to be an integer. So we have condition that bgk is integer if j or k is unfrozen. But for matrix, but for part of the matrix which connects frozen variables, we don't have any condition. So this part of matrix do not appear up to now, do not appear in mutation, so do not appear anywhere. But it will soon appear in some form. So there's combinatorial data and algebraic data. So X, algebraic data. Is a set, is a coordinates xn, xm. More geometrically, this is a torus, C star in power m, where this x1 and so on xm are chord. In principle, one can ask why torus, but not just C. But in this story, Laurent phenomena quite often is important. So torus to allowing to invert variables is good, but other we will see. And we know the so-called mutations. Combinatorially, they connect quiver Q to, matrix B to matrix B prime, and geometrically they connect one torus. Maybe I have prepared notation. It connects one torus which corresponds to B to the torus which corresponds to B prime. Maybe better to say there's no, okay, not I and A prime, and this is seeds. Okay, let me keep B and B prime, which is not literally correct, but so we have a map from the torus XB to the torus XB B prime, and this map is a birational isomorphism. This is a birational map. This mutation, and as I stated, I think several times, this mutation is invertible. It is involutional, actually, so inverse is also mutation. Definition says that X cluster variety is a union of all this XB related to initial B by sequence of mutations and gluing using birational transformations. So we take some initial seed, some initial matrix B antisymmetric and set of variables, and this will be one chart on the X cluster variety. And all other cluster charts are obtained by the mutations. This definition may be not very useful because at least this is not clear. I mean, we have infinitely many charts. What kind of scheme it is? Is it fine? What is the topology? It gives us. There are a lot of questions remains after this definition, and since it is difficult to describe all seeds which can be obtained from initial one by mutation. So it is difficult to describe this X cluster variety just by using this definition. But anyway, this is it. Similar, one can define A cluster variety. So we have quiver, you have A variables, and you glue them through mutation. Maybe I will state it later, but up to now, one will concentrate on X cluster varieties because they have a certain geometric advantage. Namely, they have a natural Poisson structure.
Sorry, can I ask?
Yes.
But we know that like we have a relation between X variables and A variables, so shouldn't be like X cluster varieties equivalent to some A cluster varieties?
There is a relation. I don't know again whether answering your question correctly, but there is a relation like this. So if you know A variables and define X variables through this formula, so X variable corresponding to some vertex G is a product of A variables which are connected in the powers of incidence matrix. Then transformation of A variables leads to transformation of X variables. So in principle, this is a relation, or more geometrically, this is a map from A cluster variety to X cluster variety. The problem is this map is in general not isomorphism, So it is neither injective, neither surjective. If Bij, if you have no frozen variables, this for which frozen variables, such formulas could be plain because in this case we don't know what is Bij. Okay, assume there is no frozen variables. But actually, we're excluding almost all examples which we had, but before. But assume. But still, this map is invertible if matrix Bij is non-degenerate. This is not quite often not the case. So there is a map, but it is in general it is not isomorphism. So there is no direct relation.
Okay, but then what? Sorry, maybe. What do we mean by frozen variables? We have them for A variables. We understand that this is variables where we don't do some mutations and which are like constant under all mutations we can do. But here in X variables we should transform all variables. So what is the notion of frozen variables?
But anyway, we have mutations which correspond to certain vertices of the quiver. And in some vertices we mutate and some do not.
Yes, but then variables assigned to frozen vertices will change under mutations, which we do in different vertices, right?
Yes, yes.
Ah,
yes,
okay. So we can't, for example, I don't know, write down some conserving variable like we have in A case.
Yes. Or, yes.
We can't. Okay.
Yes, we can.
Okay, thank you. I understand.
So in this story, frozen before they correspond to the unbounded regions. So we don't have mutations which correspond to them. They don't have any meaning. How to say in terms of the braid group relations, for example. And there will be one more reason why we don't. There will be one more difference between frozen and unfrozen in export. But again, in order to state it, I will need to introduce Poisson bracket. So definition. Cluster Poisson bracket. Defined by the formula bracket between xi and xj is equal to bij xi xj. Okay, so remarks. First, note that Bij is antisymmetric. Hence, the bracket which we just defined is also antisymmetric. Second, note that if we use not x's but their logarithms, then this formula is equivalent to the formula that logarithm of xi bracket with logarithm of xi and xj is equal to bij. If you want, in terms of the if okay, in other words, all this is equivalent that the bracket between two functions f and g is equal to the sum over all a and g, bag, xi, df over dxi, xj, dg over dxj. Or equivalent, it is equal to the baj df with respect to d logarithm of xi, dg with respect to d logarithm of xj. So in terms of the logarithm of x's, this is a bracket with constant coefficients. Hence, we have Jacobi identity. So Jacobi identity so Jacobi identity is a so Jacobi identity is you know that if you take logarithm of xi, logarithm of xj, logarithm of xk. It is, I mean, this identity for any function, but you can take just generators and such x's are coordinates. You can take generators which are logarithm of this axis, and for them this identity obviously holds because this bracket is some constant, and bracket with constant with some function is 0. So this holds, and hence it holds for any function, any functions. So this is indeed a Poisson bracket, and this is a two obvious property and most important property. I put it as a problem. That the Poisson bracket, which I just defined, is preserved under mutations. So in other words, it means that if you perform some mutation and you have some new variables, say xg prime and xi prime, then the bracket will be p prime gi, xg prime, xi prime. Okay. This, of course, is just some computation. There are, I mean, some more clever ways to do it, or more clever explanation, but maybe for the beginners, it's just a computation. Okay. There is a dual definition in terms of A varieties. Let me state it. Definition, cluster to form is sum Bij dai over I daj over ag. And the fact, maybe I also put it as a problem for symmetry, that this formula, this form is preserved under under mutations.
Do we have bracket between frozen variables also?
Here, yes, and yes, but the difference is for frozen variables, we do not assume that the corresponding b's are integers.
Okay.
And you will see that actually we will see some example where it is not integer very soon.
Sorry, and where does this cluster 2 form live?
Live on a cluster variety. So I can define a cluster variety similar to X cluster variety.
Okay, thank you.
But I should stress that this is to form, but in general not symplectic form. So if, as before, we have the matrix Bij is non-degenerate, we don't have any frozen variables, then it is the same. Poisson structure and the symplectic form are the same. But in general case, and actually in most examples which we consider, this are different stories. Okay, there is also similar problem about K2, but I will put it. I wrote the word K2 for myself, and I left it as a. Okay, so we have a natural. So if we have cluster structure, then we have natural Poisson structure. And now it's time to ask, maybe it is some non-Poisson structure. Maybe we should compare it with something. And actually, we can. And let me define the structure from which we will compare it and then state the result. I'm thinking, what is the best order? Okay, maybe the best order is like as I choose. Okay. Let us define the following matrix R, which is equal to. Okay, don't make mistakes with normalization. I look to my computations, which is equal to 1/2 sum for j less than I, Ej tensor Egi minus Egi tensor Ej. It belongs to one can write this is GLN times GLN. So it is matrices of the size n squared times n squared. This is so-called classical R matrix. It satisfies Young-Baxter equation. Maybe it's more correct to say it satisfies how it's called, modified Young-Baxter equation, which I wrote, but maybe will not use. And this is an invariant tensor. It belongs to one-dimensional space of invariant tensors. Maybe it's proportional. This invariant tensor is actually, you can take structure constant and multiply by ij and k. Okay, maybe not. Doesn't matter. This is a modified Young-Baxter, modified classical Young-Baxter equation.
Is this combination 0 or
Not.
no? Okay, so equation is that it is in invariant tensor.
Yeah, no, there is only one up to proportionality invariant tensor.
Okay, I understand.
One, I could choose it to be 0, but the price will be, this R will be not antisymmetric. Classic, I mean, in finite dimensional case, there is always some sort of price. Anyway, so this is a matrix known from the beginning of the 80s, and let me define Sklyadin Poisson structure. It's infinite Sklyadin. Okay. It is usually defined by the formula that if you take I will first write formula and then explain the notations. In terms of the coordinates, so this is the formula. In terms of in coordinates, means the following. So if you take matrix element G, I, J, and compute the bracket with some G, I prime, G prime, it is given by the following. So you compute commutator R in G tensor G, and they take from this matrix element I prime, G, G prime. The right side is a matrix of signs n squared times n squared, and here it's matrix synthesis. In more invariantly, you can say it like this. So you have R, which belongs to lambda 2 of your algebra G. Maybe I should write it even here. Belongs to lambda 2 of GLN. You have R, which can be viewed as a second exterior power of the tangent space of the identity in the group. And you can shift this R using left or right shifts. So you take, so in this formula you see you have commutator, so you have left shifts and you have right shifts. Probably the formula which I wrote is the following. So you take right shift, apply to R, minus left shift, left apply to R, and this is your Poisson tensor. Okay, this is a definition. So coordinately here, you can take any two functions on your group and compute their bracket. By this
Sorry,
formula.
so this is Poisson structure on what? On group or?
Yes.
Okay.
Maybe I should warn you that there is not only interest in Poisson structure on the group. I mean, on the Lie algebra, we know that it's actually better to take a dual Lie algebra, G star, and there is a standard constant Kirillov structure, and what else? But on the group, the story is much more interesting. And this is so-called Skleanin Poisson structure. This is, I will say a few words why this structure is interesting and why it is important, but there are other structures. For example, this structure which is called pi plus, where in this formula we have plus. And its structure also has some nice properties. There is also pi star, some sort of dual structure. So there are many other structures which can be important, and Poisson geometry related to GLN is actually a story which deserves separate one semester course. But up to now, it's a definition and theorem. First, that the pi which we defined above is indeed Poisson. And B, pi defines what's called Poisson Lie structure on GLN. In other words, the multiplication map G times G to G is Poisson. So it means that if you take on G times G, we have Poisson by vector pi plus pi. We can take its image out of the M star, and it will be just pi. And probably C states that double Bria cells are Poisson submanifold on G. And actually, unions of symplectic leaps of equal dimension. So, okay, so this is a fundamental theorem. So morally, that the fact that P-pi is Poisson structure follows from the fact that R is antisymmetric and R satisfies Young-Baxter equation. Fact that pi defines Poisson-Lie structure follows from the structure of the formula. And the fact that the commutator is a differentiation. And C, the best explanation of C, which I know, okay, best and only, uses so-called dual Poisson-Lie group and adjacent transformations. So this is a part of the story of the quantum groups, which I highly recommend, but I'm not going to, not today, not at any point of the course. I'll probably support this theorem by some more formulas and problems, but I'm not going to prove it. So I can give standard references, Cherry Presley book. Okay. And the last statement somehow somehow links us to the what we have stated before to this new structure, because before I talked, okay, we have cluster algebras, cluster Poisson structure, and now this we have some cluster structure on the double cells. And now I'm saying there is actually another Poisson structure on the double cell. Double cell of Poisson submanifold on the group, so we can take Poisson-Lie standard this Klein structure and restrict it to the double cell. And so we can ask what is it in terms of the cluster coordinates and the theorem. Which is, I believe, belongs to Fock and Goncharov. I say that the restriction of this pi on the CUV is cluster Poisson how is it structure? Yes, or bracket. Okay. Okay. I have like 8 minutes, and let me, I don't know how to say, let me behave like it's sufficient to prove this theorem. So I'm cheating, but I'm now going to prove this theorem. And the plan of the proof is the following. Due to Poisson-Lie property, it is sufficient to prove only for UV is equal to SI, where I belongs to our set of indices. I'm not very accurate here, I mean, this is a very nice point, and but I think I don't have time to discuss it in different directions. But morally, what's stated here is that Poisson-Lie property says that if you know Poisson structure in some point G and some point H, then you know Poisson structure in the product G times H. And our coordinates are given by the factorization scheme. So we just have to compute the Poisson structure on some. Then, if you know if you have factorization scheme and you know Poisson structure on the factors, then you can compute Poisson structure on the product. So, so let us consider these examples, and now we require computation, which I believe I put as a problem. There are two cases. First, if you take SI E, then in this case, your factorization scheme looks as follows. So you have H1 of x1, Hn of xn, Fn, Fi, right here for PGLN for some reasons which I'm not going to explain in a minute. Xn plus 1. So on this cell, the Poisson, the structure which was defined above, has the following form: the Sklenin algebra. X bracket between xi xn plus 1 is equal to xi xn plus 1, bracket between xi minus 1 is equal to minus 1/2 xi plus 1 xn plus 1 and here is a minus, but actually for plus the situation is the same. And all other brackets are 0. let me a bit explain this in picture. So we have, say, our sequence of lines. Now we have f. So f goes like this. Okay, anyway, no. Okay. And what is so? And we have our variables. So here is xi, here xn plus 1, here xi minus 1, here xi plus 1, and others. And what is stated in this bracket? So it's stated that here we have 1, and the part of matrix B which connects these vertices xi and xn plus 1, this faces xi and xn plus 1 with frozen vertices is actually not integer but half integer. So we have somehow two triangles glued together, two half integer triangles glued together, and they describe our bracket. So the lesson, which we should learn from this computation, that Big is not integer if Ij was frozen. It's not necessary, and I mean, and this is not just combinatorial prescription which I take from, I don't know, somewhere. This is a result of the computation. Okay, and so this is a computation for this cell. There is a similar formula for this another cell, and the generic generic cluster structure can be computed from the cell using the product or amalgamation, but okay, I'm out of time, so I will explain this next time. Okay, my time is up, so questions, so we just talk.
Probably we have as well like cleavers which do we have cleavers which do not correspond to some cells?
Theoretically?
No, from combinatorial point of view, it seems like yes.
Of course, yes, we can imagine.
Okay, and do we have generalization from some other side? We had GLN, for example, we can consider, I don't know, different groups.
Yes, there is a story for cluster coordinates on double Bria cells. It works for any type. For G2 or for E8, whatever you want. I'm just, so for example, here, for simplest case, you can see I minus 1, I plus 1, you actually, okay, so here you can recognize Cartan matrix. This number, so similar story will be for simplest case, and for non-simplest case, you actually need some generalization of the cluster algebra story. where your matrix B is not symmetric but symmetrizable. But also the story is.
But there will be still some quivers which are not correspond to some groups.
Of course, no, I mean.
Okay.
In this case, for example, we don't have, I think, more than three. All in this case, all vertices will have valency non more than 8. And 8 it's for some, not for type A, for type D or for type E. And in principle, you can imagine quivers where vertices have valency 100.